Have you ever wondered what the big deal is with integration? It's often taught as a list of rules to memorize, but it's actually one of the most beautiful and powerful ideas in all of mathematics. To get a feel for why, let's solve a puzzle together. Imagine a tank. It's 5 meters tall and 1 meter in diameter. Let's say it's filled with water up to the 4-meter mark. Down at the bottom, there's a small tap, just 10 centimeters wide. You open it. How long will it take to drain? Simple question, right? You might think just take the total volume of water, divide it by how fast it flows out, and there's your answer. That's tempting, but there's a catch. The flow rate isn't constant. Let's visualize that. If we plot the water height h on the y-axis and the outflow velocity v on the x-axis, a principle from physics tells us the velocity is proportional to the square root of the height. And when we draw that relationship, it doesn't form a straight line. It curves. And that curve is exactly why our simple formula fails. When the tank is full, water rushes out quickly, but as it empties, the pressure drops, and so does the speed. So what do? Forget the whole tank for a moment, just focus on one infinitesimally thin slice of water. Let's call its height dh, a tiny change in height. At that moment, the flow rate is nearly constant. The time it takes to drain that little slice, let's call it dt. Since the water leaving the tank equals the water disappearing from inside, we can relate dt and dh with a neat equation. Substitute the right formulas, cancel a few terms, and you get a compact expression that connects dt to dh. It tells us the time it takes to drain one specific slice. But we're after the total time. So what do? We add up the drain times for all the tiny slices, from the top all the way to the bottom. This summing up of infinitely many, infinitesimally small values, that's integration. We integrate our dt expression from 4 meters down to 0. We pull out the constants, and that negative sign, it lets us flip the limits of integration. What remains is a familiar integral, the kind we've seen in calculus class, and it simplifies beautifully. Now the rest, just arithmetic. We plug in our known values, the area of the tank, the diameter of the tap, the acceleration due to gravity. Compute the integral, and we get our answer. About 90.4 seconds, roughly 1.5 minutes to drain. So let's step back. Why was integration so crucial here? Most formulas in school assume constant rates, but in real life, like draining water, things change constantly. Integration bridges that gap. It lets us slice a complicated problem into infinitely small parts, treat each as if nothing changes, then seamlessly stitch them back together, giving us one elegant, precise solution. And that is the beautiful, powerful idea at the heart of integration.